Students, welcome to today's lecture. In today's lecture, we discussed inverse differential operator and a particular integral. In previous classes, I have discussed about the solution of homogeneous differential equations. In that, the solutions for those differential equations is what? It is a general solution. How we found? We used to find the roots by framing the auxiliary equation of a given differential equation. Okay, those are all homogeneous differential equation. Now we are studying inverse differential operator and the particular integral. Why we need these two? To solve the non-homogeneous differential equations. Non-homogeneous differential equations means what? If you have f of d into y is your is equal to some phi of x. Okay, then what is your form? F of d into y is equal to phi of x is any differential equation. If phi of x is not equal to 0, then we call them as a differential equations, non-homogeneous differential equations. Okay, now today in this class we'll discuss inverse differential operator. Already we have studied familiar with the differential operator. What is that? Differential operator is capital D. Okay, it is d by dx. This is differential operator. Okay, what is this? Differential operator. So now I'm telling it is inverse differential operator. Inverse means what? So let us suppose you have an equation, general form, d of g of x, some function, differential operator of g of x is some f of x. Then integration of capital F of x, this one. Okay, integration of f of x dx is equal to what? Is equal to gx. This is what? This is the reverse operation. Okay, reverse operation of your d. So what you can write this as? Equivalently, I can write this as, instead of this symbol, integral symbol, I can use this as 1 by d. Okay, 1 by d f of x dx is equal to g of x. So this integral symbol we use 1 by d. Okay, what it means? It means 1 by d, the operator, it is used for the, or it stands for the what? Integral sign. Okay, so integral. So which is called as, this 1 by d is called as inverse differential operator. Understood? It is called as inverse differential operator. Now, 1 by d is inverse differential operator. As in the previous differential operator, you have d square d cube. Here also, you may have 1 by d square, 1 by d cube, etc. Okay, these are successive integrals. These are called as successive integrals. And in this, we used to omit the constant here, so that we get a specific form. Suppose, one more thing you have to observe here. Suppose a is any constant, then 1 by d minus a into f of x is equal to y. Okay, then you can write this as d minus a into y equal to f of x, or You may write it as d into y minus ay equal to f of x, or you may write d as d by dx. Okay, then it is a dy by dx minus ay into f of x. So what is this? Is what? This is a linear differential equation. Okay, what is this? This is linear differential equation. So this linear differential equation, solution of this linear differential equation is called what? Particular solution, because here what it is, this linear differential equation, it is in the non-homogeneous form, because in RHS we have some f of x. Okay, solution of this non-homogeneous function is what? Particular solution. That is called particular integral, or you can call it as particular solution. Particular integral or particular solution. So what it is that? How you represent that? Particular integral pi. So symbolically it is yp. It is phi of x divided by f of d for the given differential equation. Okay. Particular integral is for the non-homogeneous differential equations. Actually, we have 5 specific forms of particular integrals which are all well defined or well established results and are readily available to solve the problems here. Okay, just I am giving you brief of those two. What to find the now for non-homogeneous differential equations, the general solution will be given by sum of two solutions. What is that? First one, complementary function, or we used to write it as yc plus particular integral, what I have discussed now, that is yp. These two, sum of these two gives us general solution for differential equation of non-homogeneous type. Okay, so we'll discuss them both the forms in brief. Just we recall that, because already you know how to find that complementary solution, that is complementary function. Means what? We have to solve non-homogeneous differential equations in two stages. In stage 1, we have to find complementary function. Okay. So solution of f d of y equal to phi of x. Okay. That is non-homogeneous differential equation. We have to solve it in two stage. In stage 1, we have to find complementary function, that is yc. How? By solving p of y equal to 0. We making it equality to 0, means RHS to 0. How? When you equate it to 0, we have to frame auxiliary equation. Okay, we have to form a auxiliary equation. Okay, what is the first step? Form the auxiliary equation. What is that? Auxiliary equation, replace d by m. That is what? F of m equal to 0, and will solve. What will you get? Will get the roots. Okay, that is what? CF is based on nature of roots. Okay, nature of roots. What is the nature of root? Just recall, in the previous classes I have discussed these. So depending upon the nature of roots, there are three types we have discussed. Suppose you'll get the roots m1 and m2, which are real and distinct. Okay, then what will be the solution? Complementary function. It is C1 into e raised to m1x plus C2 into e raised to m2x. Roots are real and distinct. What is this? This is a complementary function. Okay, it is nature of auxiliary roots. Second, if the given roots, the whatever roots obtained, those are equal. What are called as? They are coincident roots. What we call them? We call them as coincident roots. So then the complementary function is C1 plus C2x into e to the power mx. Third type is, in this, suppose given roots are plus or minus I into q. What are these? Are complex roots. Okay, pair of complex roots. If roots are complex, then the solution is e raised to px c1 cos qx plus c2 cos sin qx. This is the complementary solution. Suppose the given pair are imaginary roots. Means what? There is no this real form. Real, only imaginary part we have. Real part irudilla. So plus or minus iq. So this is imaginary root. So then the form of solution is C1 cos qx C2 sin qx. Means what? This part will not exist. That's it. Only simple way. This is summary of what? This is summary of to find the complementary function. This is stage 1. Then in a stage 2. So stage 2, as I mentioned, we have 5 standard forms of particular solution. Okay. Now stage 2, to find a particular solution of what? Of your non-homogeneous differential equation, which is of the form f of dy equal to f phi of x, or particular integral, how we write yp is equal to phi of x divided by fd. This is a solution. This is y is equal to phi of x by fd. So here we have 5 types. Okay. In the first one, the type 1 is e raised to ax divided by f of d. If it is your yp is of the form this form. So here only e raised to x, not only e raised to x, you may, in place of e raised to x, you may have e raised to ax plus b, a raised to x. This is nothing but e raised to log a into x. This one, and also you may have hyperbolic function sin hyperbolic ax, cos hyperbolic ax, all these. You may have all these in place of e raised to ax. This. If your function is of this type, then what happens? How you find particular integral? Then if function is e raised to ax by f of d, then replace d by a. Okay, such that f of a should not be equal to 0. What we did? Replaced d by a. Okay. Then this is what? If a not equal to 0, we have to stop here. Suppose if f of a equal to 0, we have to continue. Means what? If f of a becomes 0, then we have to differentiate this e raised to ax. Sorry, the formula is x into e raised to ax. We have to differentiate the denominator, that is f dash of a. You have to continue. Suppose again f of a is 0, then x square into e raised to ax f double dash of a, and so on. This is for f of a equal to 0. This is for f dash of a equal to 0. Okay. This is how to find the solution. That is a particular integral for e raised to ax by f of d form. Second form is function is of the form sin ax by f of d square or cos ax by f of d square. Means what? It is applicable for ax. Instead of ax, you may have sin ax plus b, cos ax plus b, and sin ax cos bx, sin ax sin bx, or you may have cos ax cos bx into, and by you may change them into sum, changing into sum. Okay, you may have all these forms here in the numerator. In such cases, what will be the particular integral? First step is keep numerator as it is, replace f of d square by minus a square. Okay, cos ax by f of minus a square, where f of minus a square should not be equal to 0. Okay, what we did? D is replaced by minus a square. Again, if f of minus a square is 0, if f of minus a square is 0, then what happens? Then x into sin ax divided by f dash of minus a square. Okay, if f dash of minus a square is 0, then x into x square into sin ax by f double dash of minus a square, and so on. Same things will be extended for cos ax. Okay, this is second type. Now in third type, function will be of the form phi of x divided by f of d, where phi of x is a polynomial in x. So polynomial in x. So then what will you do? We divide phi of x by f of d by writing phi of x in descending powers of x. Okay. So dividing, what will we divide phi of x by f of d by writing the phi of x in descending powers of x. And what will we do next? We'll do f of d in, we have to write f of d in ascending powers of d. We have to write phi of x in descending powers of x and f of d in ascending powers of d. Then the quotient is equal to particular. And this remainder will be 0. Remainder will be 0. This is how to solve the functions if you have phi of x is a polynomial. Fourth form, if you have e raised to ax into v divided by f of d, where v is v of x. So in such case, we have to write e raised to ax v divided by some function f of d plus a. Okay, d is replaced by what we'll do? D is replaced by d plus a. And what will then we find v divided by f of d plus a v multiplied by e raised to ax. Okay. First we replace d by d plus a, then we find v by f of d plus a, which will be pre-multiplied by e raised to ax. Fifth type, x into v divided by f of d, such that v is equal to v of x. In such case, particular integral will be of the form x minus f dash of d divided by f of d into v divided by f of d. This is another form, last form of particular integral. These are all 5 types of particular integrals, and so these are the right side of the, these are all solution or methods to getting the particular integral. These are type of particular integral. Okay, when we'll go on solving examples on all the types, so that you will get how to use these methods to get the particular integral, and as well as solution of the given non-homogeneous differential equations. Okay, in the next video I am going to solve examples on type 1. What is type 1? Type 1 is e raised to ax by f of d form solutions. We'll see how to use these methods. Okay, till then keep practicing. If you have any doubts, please comment in the comment box. Take care. Thank you.